Good evening to everyone. So now we are going to solve a numerical problem on open cycle gas turbine with reheating, right? So let us see a problem. The following data refers to gas turbine plant. Power developed equal to 5 megawatt. Inlet pressure and temperature of air to compressor equal to 1 bar and 30 degrees Celsius. Pressure ratio of cycle equal to 5 bar. Isentropic efficiency of compressor equal to 80 percentage. Isentropic efficiency of turbine equal to 85 percentage. Maximum temperature in turbines equal to 550 degrees Celsius. Cp for air equal to 1 kilojoules per kilogram Kelvin and gamma for air equal to 1.4. Cp for gases equal to 1.15 kilojoules per kilogram Kelvin and gamma for gases equal to 1.33. And if reheater is used between two turbines at a pressure of 2.24 bar, calculate the following: mass flow rate of air and the overall efficiency of the cycle. Neglect the mass of the fuel, right? So this is the problem. So first we have to draw the schematic diagram. The schematic diagram, you have to explain what is the process, you have to infer what is the process happening. So here air enters this compressor at 1 bar and 30 degrees Celsius, right, and leaves at a 5 times higher pressure because pressure ratio is given as 5, right? So it leaves the compressor at 5 bar and at a higher temperature, which we have to find out, and combustion takes place. And after the combustion, the temperature of air will be increased and the air will be converted as combusted gases. The combusted gases will pass to the high pressure turbine, where it gets expanded to a lower pressure, which is 2.24 bar. Intermediate pressure is given as 2.24 bar and a lower temperature, right? So this lower temperature air is again reheated to temperature which was before expansion and then sent to the second turbine, where it is compressed back to 1 bar pressure. So work output is produced in turbine 1 and turbine 2, and work input is given in compressor. Heat input is given for combustor and reheater, right? So here we are having two different Cp values. In the question we are having Cp for air as 1 and gamma for air as 1.4, and Cp for gases as 1.15 and gamma for gases as 1.33, right? So let us see why. Here during compression process alone there is air. Once the air enters the combustion chamber, it is converted to gases. So Cp for air should be used only for compression. For rest of all the processes, we have to use Cp for gas, as the air is converted to combusted gases once it enters the combustion chamber, right? So now we will see what is the given data. So given data is that pressure 1 is 1 bar, that is pressure at the start of compression, and temperature at the start of compression is 30 degrees Celsius, which is 303 Kelvin, and pressure ratio is 5, therefore pressure after compression will be 5 bar, right? So intermediate pressures P4 and P5 will be 2.24 bar, and the maximum temperature of cycle T5 and T3 will be equal to 550 degrees Celsius, which is 823 Kelvin, and isentropic efficiency of compressor is 0.8 and isentropic efficiency of turbine is 0.85. As we said earlier, Cp for air is 1 and gamma for air is 1.4, and Cp for gases is 1.15 and gamma for gases is 1.33. Here is the TS diagram. Here as we already seen in many of the previous problems, 1, 2s, 3, 4s, 5, 6s is the ideal cycle, whereas 1, 2, 3, 4, 5, 6 is the actual cycle. In the ideal cycle, the compression and expansion process will be isentropic, whereas in the actual case it will not be isentropic. And for compressor, minimum work required will be calculated using isentropic temperatures, and for turbine, maximum work that can be derived can be calculated using isentropic temperatures. Now we will see component by component. You have to solve component by component. Now for compressor, using isentropic formula, we are calculating isentropic temperature as 479.9 Kelvin, right? Now compressor efficiency will be equal to isentropic work. Isentropic work for compressor is minimum possible work divided by actual work. Using that formula, we are getting temperature after compression, actual temperature after compression as 524.12 Kelvin. So compressor work is Cp for air, as compressor inlet and outlet both are containing air. We are using Cp for air into T2 minus T1, which is coming as 221.12 kilojoules per kilogram. Then we are moving on to high pressure turbine, right? In the high pressure turbine, expansion takes place from pressure 3 to pressure 4. Therefore, T4 is equal to T3 by P3 by P4 whole power gamma minus 1 by gamma. So P3 is 5 and P4 is 2.24, intermediate temperature, and we are using gamma because in turbine the fluid is combusted gases, so we have to use the Cp and gamma values of combusted gases, right? So T4s isentropic temperature is coming as 674.33 Kelvin. Now turbine efficiency is equal to actual work divided by maximum possible work. Isentropic work is maximum possible work, right? So actual work by isentropic work. So actual T4 is coming as 696.63 Kelvin. So this is regarding the high pressure turbine, right? So next we have to move on to low pressure turbine, where T6 is equal to T5 by P5 by P6 whole power gamma minus 1 by gamma for exhaust gases, right? 823 by 2.24 by 1. Inlet temperature of the low pressure turbine is 2.24 and outlet temperature of low pressure turbine is 1. So T6 isentropic is coming as 673.74 Kelvin, whereas turbine, using turbine efficiency, we are finding T6 as 696.13 Kelvin. Now we found out the work done by, the temperature for high pressure turbine and low pressure turbine. Now we have to find out the turbine work, which is the summation of high pressure turbine work and low pressure turbine work, which is coming as 291 kilojoules per kilogram. Now we have found out the turbine work. Now we have to find what is the heat input. If you see the schematic diagram, heat input is given in two processes, that is from 2 to 3 in the combustion and from 4 to 5 in the reheat. So at two stages we are giving the heat input, right? So heat input will be equal to Cpg into T3 minus T2 is heat input given for combustion, and Cpg into T5 minus T4 is heat input given for reheat. So total heat input is coming as 489 kilojoules per kilogram, right? Now next we have to find what is the net work. Net work is summation of all the works in the system. In this system, work refers to three components, that is compressor and two turbines, right? In the compressor we are giving work from our side, so it is the negative work. In turbines we are deriving work, so in turbines we are deriving positive work. Therefore W net will be equal to W turbine minus W compressor, which is coming as 69.88 kilojoules per kilogram. Now we have to find the reheat cycle efficiency, which is nothing but W net by heat input, which is coming as 0.1428 or 14.28%. Now we have to find out the mass flow rate of air. We can find by the formula power equal to mass flow rate into W net. Mass flow rate is coming as 75.5 kilograms per second. So here efficiency of reheat cycle is 14.28 and mass flow rate is 75.55. So here we are reheating the air. We are giving heat at two places. So we are giving more heat, but the work is almost same because we are compressing from 1 to 5 bar. Again, using two turbines, we are expanding it back to 5 to 1 bar. Therefore, efficiency is little bit lesser when you compare it to regeneration, right? So this is the problem regarding gas turbine cycle with reheat, right? Thank you.